Take a look at the mathematics of growth. The generation time is just the time required for the population to double in size. And this can vary depending on the species of microorganism and also on the environmental conditions, because if the temperature isn't right, or maybe there's not enough nutrients, maybe they're not going to divide as quickly. So we've got this formula here, which is really important and we're going to be working with in just a minute. And so what we're going to be solving for is n sub t. So this is just the number of cells after a certain amount of time. And n sub 0 is just the number of cells that we're going to start with. And then we're going to multiply that by 2 because the population is going to be doubling in size every generation. So that's why there's a 2 in our formula. And then we're going to raise that to the power of t divided by d. And t is just the amount of time that's passed, and d is our generation time. And the reason they put a d there is because the population is going to be doubling in size every generation. And then here's just a little table here, just showing you that we've got a generation time of every 20 minutes. And you can see that the population is going to double in size every generation. So you start with 1 cell, doubles to 2, and then that'll double to 4, and so on. Okay, and here's just a visual representation of those numbers. So if you start with 1 cell, then the next generation you would double in size and get 2 cells, and then the next generation those 2 cells would each divide, and then you'd end up with 4 cells. And then the next generation, each of those 4 cells would divide and you'd end up with 8 cells. And then next generation you get 16, and then they double again, and then you get 32. All right, so here we've got, starting with our first generation, we're going to start with 1 cell, and we're going to go to 20 generations. And so from that 1 cell that we've started with, we're going to end up with over 1 million bacterial cells. And then we've also taken the log of the number of cells here as well. And so we're going to graph these numbers. And on the bottom, we've got the number of generations. And over here on the right, we've got the number of cells. So here we've just plotted the number of cells with the solid line. And then over here on the left, we have the log of the number of cells. So when we plot the log of the number of these cells here, we get this dashed line, and note that it's a diagonal line. And anytime that you see a diagonal line like that, it just means that the population is doubling every generation. You've got this exponential growth. So to answer our question here, during which phase of the growth curve do we get this exponential growth, or the population doubling every generation? That's going to occur during what we call the log phase. Okay, so it's log with an O, and that's when we're going to get the doubling every generation of the population. All right, so let's work with our formula here. So let's say that we start with a population of 50 bacteria, and let's say the species of bacteria has a doubling or generation time of 30 minutes, and the time that's passed has been 90 minutes. So we want to know, well, what's the number of bacteria after 90 minutes if we've started with 50 bacteria? So with our little formula here, we're going to be solving for n sub t. And we know that the number of bacteria that we started with was 50. And then we're going to multiply that by 2 because our population is going to be doubling in size every generation. And then we're going to raise that to the power of t divided by d. And then the t is just the amount of time that's passed. So it's been 90 minutes. And then we're going to just divide that by the d, which is our doubling or generation time. So that's been 30 minutes. So we're just going to rewrite this, and it's 2 raised to the power of 3. and 2 raised to the power of 3 would be 8. So our answer is we would have 400 bacteria after 90 minutes if we started with 50. Okay. And so the biggest mistake that I see when I have a question like this on the test is people will forget that it's 2 raised to the power of 3, and they might say, oh, that's 2 times 3. And then that's where they mess up and get the wrong answer. Another mistake I see is that they'll flip these numbers and they'll have 30 on top and then 90 on the bottom. And so if you ever get, not a whole number here and you get like a decimal, that you've done something wrong. You've probably flipped the numbers. So you should get a whole number here, and then just raise that to the power and don't multiply that. So that's the other mistake that I'll see. Okay, so let's just do another one. So let's say that we start with 1,000 bacteria, and the doubling time for this species of bacteria is 20 minutes. And the time that's passed is 80 minutes. So we want to know the number of bacteria after 80 minutes. So we're just going to solve for n sub t. And n sub 0 is just the number of bacteria we started with. So we had 1,000 bacteria. And then we're going to multiply by 2 because our population is doubling in size every generation. And then t is just the amount of time that's passed. So that's 80 minutes. And then the d is the doubling or generation time, so that's 20 minutes. And so if we rewrite this, we have 1,000 times 2 raised to the 4th power. And so it's going to be 1,000 times 2 raised to the 4th power is 16. So our answer will be 16,000 bacteria after 80 minutes. Okay, so there will be homework problems like this, and then I will put a test question like this. Well, you'll need to solve for n sub t and give you information to plug into the numbers, the formula here. So I'll give you the formula, but you just need to know, what the things stand for to make sure that you plug in the numbers to the right places here to solve for that. So this graph is just showing you how to determine the generation time, which is what you guys were doing in lab. And we've just plotted our number of bacteria, the log of the number of the bacteria, and we've had them growing in the log phase, so they've been doubling in their population number every generation. And you can see the log of the number of the cells, and you can see where they've doubled. So 0.5 to 1, they've doubled in number. And what we've done is we've just gone where the population has doubled, and then you can just measure, well, how long did that take to double? Okay, and that would be your generation time. Unfortunately, this is in hours, which is a little bit difficult for bacteria because usually they're going to be doubling in minutes. So here we've got a table here with some generation times. Here's for bacteria. And unfortunately with hours, it's a little bit difficult to interpret, but if we have 0.35 hours, that's about 20 minutes for E. coli. And for Staph aureus, we've got a generation time of half an hour. But other ones are much longer, like Mycobacterium tuberculosis takes about 12 hours to divide, and Treponema pallidum that causes syphilis is over a day, 33 hours to divide. The other thing I want you to notice, we've got some eukaryotic microorganisms. We've got some protists here and some fungi. And notice that their generation times are in general going to be much longer than the prokaryotes. And the reason that is because the eukaryotic cells have a lot more DNA to copy. Okay, because remember the DNA replication, that is your limiting speed for how fast you can divide. And also the eukaryotic cells have to do the whole mitosis thing, do the mitotic spindle, and that's going to add to their time as well. So in general, the eukaryotic cells are going to divide much slower than the prokaryotic cells because the prokaryotic cells don't have as much DNA to replicate.